For today's webinar, we have Jeremy Morris from the Johnson County Sheriff's Office presenting a forensic analysis of cosmetics. Without further delay, here's Jeremy.
Good afternoon, everyone. Thank you so much for setting aside part of your day to talk about forensic analysis of cosmetics. As already mentioned, my name is Jeremy Morris. I'm with the Johnson County Sheriff's Office Crime Lab. I've been here since about 2003. Had a varied career in drugs and trace and lesbian pattern analysis. So today we're going to just talk about makeup. So I want to thank the Forensic Technology Center of Excellence for allowing us to have this opportunity. So we're going to do a quick overview of kind of a little bit of a roadmap of where we intend to go. We're going to do a brief introduction to the composition of cosmetics. We're going to focus really though on those cosmetics that are applied to the face, makeup and foundation and other powders and lipstick and lip gloss. We're going to talk about some analytical techniques that are for these submitted materials and kind of deal with a couple questions that I had with my case that I first ran into. The first one is, this material a cosmetic? How can we go about answering that specific question? And if we were able to make that determination and then to look at a question and known comparison, some limitations of those types of comparisons that are specific to the samples as well as the products and other specifics of the material. So we're going to kind of move through these things rapid fire, so hold on. But I do need to kind of do some full disclosure. I am not an expert in cosmetics. Cosmetics are not something that I wear on a routine basis. I think I've only wore them as far as Halloween makeup in my head red one time. Some of you may remember that. So I don't really have my own personal use background on this. So then you may ask yourself, then how in the world did I even get involved in cosmetics? A few years ago, we had a case. It was a death investigation where cosmetics were in an area that should not have been. And so I was asked if the material that was being used to cover up injuries was a cosmetic, if I could make that determination. And if I could, if there's any way, then I could compare the material that was collected from over these injuries, if I could compare it to known cosmetics that were collected from the scene. So I never researched it. So that kind of started a research project that began internally, getting materials from various ladies in the lab. Then that kind of expanded into looking into materials that are placed in cosmetics, reaching out to suppliers of those materials. And I had a very fortunate encounter with a cosmetic chemist with Brentag Specialties. A little shout out to Christina Dean. She is a rock star. She was so incredibly helpful and kind of opened up my eyes to all of the wonderful things that go on into formulating cosmetics. So that's a little bit how I got into this. So the first question is, what are cosmetics? What are these materials? We use this term and, loosely, and I think we have an idea of what they might be. We think of those things that are like makeup and powder and highlighters and bronzers and all these things that you ladies are very much aware of. FDA, the Federal Food and Drug and Cosmetic Act actually defines what cosmetics are, that they're articles intended to be rubbed, poured, sprinkled, or sprayed on, introduced into, or otherwise applied to the human body. They can be used for cleansing, beautifying, promoting attractiveness, or altering the appearance. This is a really, really broad definition and captures a lot of things that we may not necessarily consider traditional cosmetics, but they do fall under this definition. So it includes skin moisturizers, perfumes, lipsticks, fingernail polishes, eye and facial makeup preparations, and to get into the world of shampoos, permanent waves, hair colors, hair dyes, toothpaste, deodorants, and so on. So a lot of products that are covered under this definition. And most of those we're really not going to deal with today. Today's discussion is going to be limited to what we typically refer to as makeup, things that are applied to the face. We're not really going to touch on a fingernail polish or hair colors or hair dyes. But if you think of something that is considered makeup, you go into the makeup aisle, then that's kind of what we're going to touch on a little bit today. So what are the things that are added to formulate these cosmetic products? And there's a whole host of things. And trace chemists are very much aware of variety and formulation of products, that the end use of the product often dictates the materials that are placed in that product. The end use of a paint sample dictates how that paint sample is formulated, whether we're talking about an architectural paint, an automotive paint, or a spray paint, or even marine paints, and so on. And the same thing applies to the world of cosmetics. The intended product purpose, is it going to be a foundation? Is it going to be a blush, a concealer, fingernail polish, lip gloss, lipstick? Those things, the intended purpose is going to dictate the materials that are placed in it. The mode of application, are we talking about a brush on powder? Are we talking about a liquid foundation that is smeared on? How is that product going to be applied to the skin? And then the desired properties, as well as the cost. And the cost can be a fairly significant factor in determining the kinds of materials that are placed in a product. And often not just the kinds of materials, but the quantities and the specific concentrations of the relative concentrations of those materials. And as we go through and look at an ingredient list, if your background is in paint or in polymer analysis, such as tape, you're going to recognize some of these materials. So they're going to look familiar, but we need to be careful with that, because once some material is designated for use as a cosmetic, because it is being applied to the human body, there are all sorts of other regulations that come into play. So even though the name looks the same, that doesn't necessarily mean that the material is going to look the same microscopically or even analytically. And we'll touch on some of those examples. So we're just going to go through a few examples of the composition of various cosmetics. And you can see that these can be fairly extensive. According to the FDA regulations, if there is a product considered an active ingredient, that active ingredient must be listed first. So here, titanium dioxide is considered an active ingredient as a sun blocker. So that is going to be listed first. And then all other inactive ingredients are listed afterwards. So what I've done is I've highlighted materials that in other areas of trace evidence that we may recognize. Titanium dioxide is clearly one that we run into a number of different times. Dimethicone is going to be that polymethyl siloxane that can be run into in condom lubricants. And nylon 12 and other polymer analyses, sodium chloride, alumina. And then here this list at the end may contain, and we see this fairly often in ingredients, and it's just essentially saying, depending on the formulation, depending on the shade, it may contain a variety of materials. Mica, titanium dioxide, iron oxides. And what we're going to see is that even though those are listed separately, the mica, titanium dioxide, and iron oxides may be mixed together as individual particles. The iron oxides may be electroplated on top or coated onto the mica, as well as the titanium dioxide, or they may be completely separate. And what we can see is different shades are going to have different ratios of this. So if we go to different shades of the same formulation, the only difference between those different shades may be the iron oxide concentration to get a lighter or darker hue or color. So now as we look at the powder foundations, we're going to see that we've got some differences. We have some similarities in the formulations, but we also have some differences. Because we have a powder foundation, we no longer have many of the liquid components that were part of the liquid foundations. Now we have talc and mica silicon, again, dimethicone, nylon 12, glycerin. Glycerin is a liquid, but it's listed lower on the list. And then we also have that list of may contain, again, the iron oxide, TiO2. And now we have different ones, bismuth oxychloride, as well as red 7 lake. And here we have a red pigment that can be part of this powder foundation. Moving on to lip gloss. This will be the last one that we look at the composition. The ingredient list here, again, is fairly extensive. We have that at the bottom that may contain list as well. We have some additional lake pigments in there. But the highlighted section here, what I wanted to focus on here is a lot of the oils and waxes that can be in lip glosses as well as lipsticks. These can be a fairly sizable component of these specific materials, and we can have synthetic waxes and oils, or we can have those from natural sources. And here we have waxes and oils that are from a variety of seed sources. And those are going to come into play in how we visualize those, or how we actually see those in our various analytical techniques. Specifically, they're going to show up in infrared examinations. So before we move on, just a few more thoughts about the ingredients. As we go, I'm going to take a step back here. And if we look at this ingredient list again for the lip gloss, the ingredients are listed in decreasing order of prevalence. So the most prevalent component within the formulation is going to be listed first, and number 2 is listed second, and so on. So what that means is we get further and further down the list, it becomes less and less predominant within that formulation. Now that can change when you get to the list of may contain, because those are the various pigments. They can vary from one product within a line. So what this does mean, though, is because no absolute percentages are given unless that component is an active ingredient, all inactive ingredients are only listed in relative intensity order. So you can have 2 products with identical ingredient lists, but they have completely different formulations. So what that means is that we can't compare ingredient lists to see if 2 products are identical, because we have one product that lists water first, and it may only have 30% water as far as its composition, and the next one has water first, and now it is 70 to 80% water. So vastly different concentrations of water within those formulations, which means that those products are actually not going to be the same. So we just have to be aware that products with the same ingredient list do not necessarily mean that they are the same formulation, which means analytically they can look completely different. And also, as I mentioned before, cosmetics may use the same materials as more traditional forms of trace, but they can be very, very different. FDA regulations, as I mentioned before, are going to address the quality and impurities and other factors that are related to those materials. that, quite frankly, those who are in paint formulations or adhesive formulations don't care about. And then we have additional processing techniques that are specific to cosmetics. Whereas, if you have something like talc that is used primarily as a filler or other agent within tape, when it comes to cosmetic, it is a completely different purpose. The specific form of talc that's used can be completely different than the form of talc that's used in other traditional forms of trace. And processing techniques can make it so that talc looks completely different microscopically to us. So just because it's on the ingredient list doesn't mean that we're going to find it during the analysis. This is particularly true for those that are way down on the ingredient list. It may be particularly difficult for us to detect things that are less than 1%, and it also may be that the materials are evaporate away, that they are absorbed, or that in IR, the spectral bands of those materials are going to be masked or overlap with spectral bands of other components. So the ingredient list is really there to kind of give us an idea of the materials that are present, but don't really develop much of an expectation that you're going to be able to find everything that's on an ingredient list. So when I got into my initial work into cosmetics, I went to the literature to kind of give me some help and guidance on methods to discriminate, batch-to-batch variation, methods to discriminate different sources, ways to kind of do my analysis. What I found is there really isn't a lot out there. And the publications that are out there are really kind of focused primarily on lipsticks as well as foundations. And there are a few papers here and there that deal with other cosmetic products, but these two general products are really the bulk of the literature that's out there. So the next couple slides are just going to give a quick overview of some of the publications that are out there. We're not going to go through these. This is really just for your information. If you would like to have a copy of this slide and the next slide, you're more than welcome to email me, and I can go ahead and send you copies of these slides so that you can reach out and find these articles yourself. As we look through these, we can see that there's a variety of techniques that are listed. The primary techniques are going to be spectroscopic techniques. We've got infrared as well as Raman spectroscopy that are used. We have one paper there in the middle that talks about PIGC MS on lip glosses. Admittedly, this is something that I was interested in looking into with my own samples, but I just ran out of time. The next slide deals with foundations. There's not really as much information out there in the literature regarding the analysis of foundations as there is with lipsticks, and it may just be because of the nature of foundations that we just don't define themselves. They're going to be a mixed product as the foundation is applied. Other products are then applied on top of that. But there are a few papers that are out there that deal with different ways of differentiating and analyzing cosmetic foundations. All right, so let's get into the various ways of doing an analysis. These are the three techniques that I used in my case. So they were the ones that I researched the most: IR, SEM, EDS, as well as microscopical examinations of the particles. There are clearly other ways that you can analyze this based on the instrumentation that you have at your laboratory. You can do Raman. You can potentially do MSP on colored cosmetics if you so choose, but these are the ones that we're going to focus on today. And besides them being the most available to me, there are reasons for that. IR is simple, it's non-destructive, it's a great general analytical tool that we can use to determine the organic and some inorganic components of materials. IR, if we're trying to identify individual components, is going to be a bit of a challenge for mixtures, especially for complex product formulation. Now, if we were able to approach this like paint and identify specific spectral bands that are somewhat characteristics of individual components or component categories, we can use those spectral bands in our interpretation of the IR spectrum. But really, the complex product formulations are going to be a problem. And also, trying to use IR to differentiate from one product to another just using IR is still a work in progress. Some of the papers that are published talk about that. I was an advisor on a master's student who was using this approach, trying to use ATR, FTIR to differentiate various foundation products, and found out that that's somewhat problematic. There, you can do some separations based on large groups, but individual product to product differentiating is a bit of a challenge because of how similar these products are. SEM EDS is pretty straightforward to assist in particle identification as well as particle visualization. And the microscopical, for me, this is the approach that I would take if I'm asked the question, is this material a cosmetic? Because there are going to be some materials that are just going to kind of jump out at us when we do some particle dispersion and look at them under the PLM. So the general approach to answer that question is going to be particle ID. Many of you have a much stronger background on microscopy than I do. Mine is just a few courses in intro to microscopy and intro to PLM. If you have larger questions about conoscopy and some of these other more advanced techniques and how they apply, I really don't have much insight into those. But these are the particles that we could potentially pick out when we do particle ID of dispersions of these materials. You can look at various micas. There are going to be natural micas as well as some synthetic micas. We have other larger flakes that are in there, bismuth oxychloride, TiO2, talc clay, and then we have these spheres, and we'll talk about what these spheres are, as well as some starch. And there are other components that we can run into. We're going to pick these up by IR rather than microscopy. This is polydimethylsiloxane, or that dimethicone we mentioned, lauryl lysine, as well as boron nitride. We're not going to spend a lot of time talking about the last two. We will talk specifically about dimethicone, though, and how we can interpret an IR. So let's just go one by one and look at some of the larger components. And what we'll do is we'll kind of do a brief introduction. These are going to be very familiar to those who are used to traditional trace. And we're going to talk about how they are most readily identified. So for talc, magnesium silicate, talc can come in two forms, but in cosmetics, because they want it to have a soft, silky feel when it's applied to the skin, only the plate form is used in cosmetics. So the reported refractive indices are 1.54 and 1.59. for talc, which means that if I'm mounting my sample in a mountain that has a refractive index of 1.64 or 1.66, I ought to be able to see the individual talc plates. And that is not the case at all, at least in my experience, and I have absolutely no idea why. I would have a material that the primary component of that material was talc. The only thing that I could see on the IR was talc, those very distinct spectral bands. But when I looked at the mounted preparation under the microscope, the talc particles simply did not jump out at me. They were very, very difficult to see. And I don't know why that is. And I've asked about that, if there's any annihilation processes that are applied that would affect the refractive indices, and I just haven't gotten a satisfactory answer. But for talc, it's going to be most readily identified by the IR spectrum. So this slide here shows you just a photomicrographs of 4 different talc samples. And these all had IR spectra that were the same. They showed the hydroxyl stretch that we use for talc. So I knew it was talc as well as with other bands, but I simply could not see it as well as I was expecting to see it in my microscopical preparations. And again, for all of these, the mountain is going to be a 1.64 refractive index. So this here is the IR of talc. The specific band that we're going to look at is on the far left side. This is going to be the 3676. That is an OH stretch that is fairly unique to talc. Once you start replacing your magnesium with other cations and you start having a shift of that hydroxyl stretch, not only do you have a shift, but then you start having splits, that single peak splitting into other peaks. But here we can see that we've got talc from various different sources as well as various different compositions, and the spectrum is pretty much the same. We have 2 large peaks on the right-hand side, and then that small diagnostic peak is on the left-hand side. So for mica, this is another plating mineral that's going to be applied to various products, but instead of being applied for the purpose of the feel of it, instead of having a soft, smoothie feel, the mica is going to be applied to give us a specific visual effect. This is going to be applied for the shimmer or the glitter. So when we look at natural mica, these are going to be potassium-rich particles, so potassium aluminum silicate. The reported refractive indices for natural mica are in the 1.55 to 1.58 range, but we will never see particles that are in this range. And that's because mica is used as the base for various metal oxides to be deposited on those. So those metal oxides can include titanium dioxide as well as iron oxide. And because the metal oxides have a significantly higher refractive index, that's going to affect the refractive index of the particles that we see. So don't use your refractive indices of mica to guide you in your determination of whether a material has mica in it. These particles are going to jump out at you when you look at the microscopical prep of them. And what you're going to see is you're going to see all kinds of colors. In paint exams, we're used to seeing these in the effect pigment that are in the color coats or the base coats of vehicle paint. And we see, so and you think of what that looks like, you're going to see those pastel colors, and we see those same kinds of things here. But you're going to see even more than just the pastel colors. Depending on the thickness of the iron oxide as well as the type of iron oxide that's applied, you can get different colors, and we'll talk about that with the next slide. The key feature for the identifying mica plates is going to be the irregular and rounded shaped edges. That's going to help us differentiate mica from borosilicate glass flakes. So as we look at the coating that's applied to mica particles, these are the metal oxides. And depending on the specific metal oxide that's applied, as well as the thickness of that layer, that's going to determine the color that we see that comes from that metal oxide. So here there are 2 types of products that are marketed out there. One is a bright silver, the other is a Tamika Rouge. And what we can see is that they have visually different appearances to those. We have the various pastels that are on the left-hand side. Whereas on the right-hand side, we have the red to brown, red oranges, deep oranges. And that's because it's a different kind of metal oxide. We have titanium dioxide that is on the left-hand side and iron oxide that is on the right-hand side. And you can even have combinations of both of those, and not only combinations of both of those on a single mica particle, but you can have mixtures of different micas with different ion oxides within the same sample. So here's the IR spectra of mica. And we're going to see a pattern here. We're going to see a lot of IR spectra that have strong peaks around the 900 to 1100 range. And this is going to be the typical range for the silicone oxygen stretch, which means it's going to be difficult for us to do much interpretation in this range. But the different products have essentially the same IR spectrum. So now let's look at the synthetic mica. This is synthetic fluorophlogophite. And instead of a potassium rich aluminum silicate, this is going to be a magnesium rich aluminum silicate. There is potassium that's present, but we have a lot more magnesium in these samples than what we have in the muscovite micas. And this is synthetic because what they've done is in addition to replacing some of the potassium with magnesium, we also have a replacement of the free hydroxyl groups with fluorine. And so that is going to be a key feature that we're going to use in the elemental analysis of particle identification, is to look for the presence of fluorine on visual particles. So other than that, they are identical to natural mica for our purposes. I was able to teach a workshop on cosmetic analyses a few years ago at Midwestern Association of Forensic Scientists. And the question came up about what the iconoscopy is for this material. And I only have the briefest introduction to iconoscopy. So there may be differences, but I'm just simply not the one to be able to answer that. But when it comes to synthetic mica, this is most readily identified. You're going to see it via microscopy, but it's going to look just the same as the natural mica. It's going to have the same colors, the same sizes. It's also microscopically, it's going to have those rounded, irregular shapes. But to differentiate the synthetic mica from the natural mica is going to require SEM-EDS analysis of the individual flakes. You have to focus your electron beam on individual flakes and look at the spectra and look for the presence or the absence of fluorine in those samples. The reason why manufacturers or formulators would use synthetic mica is because you have a lower lead content, and there are some regulations that a super low lead content is going to be required for cosmetics that are applied to specific areas of the body, such as around the eyes as well as the lips. So this is what synthetic mica looks like with a photomicrograph. Again, if we were to put this sample and the natural mica side by side, we're not really going to see much of a difference between those two. And here again is the IR spectra of natural and synthetic mica. One of the things I look for is because we do have the presence of fluorine. Those free hydroxyls have been replaced with fluorine. We do have some minor changes. We can see that the OH stretch that is weak in natural mica is completely gone in the synthetic mica because those hydroxyls have been replaced with fluorine. So I was looking for fluorine carbon stretches, and if they're present, they really just don't jump out. And even if they were present at low levels, once you have this product blended in a formulation, we're likely going to lose those bands. So the big thing is going to look at the elemental analysis. We have natural mica on the top, and then we have synthetic mica here on the bottom. So I want to draw your attention to two specific areas on the synthetic mica. We have a significantly higher magnesium content than with natural mica. In fact, the magnesium has replaced the vast majority of has replaced some of the potassium, but replaced most of the aluminum. But the big thing there is going to be the fluorine. The fluorine is not present really at all in natural mica, but it is in the synthetic mica. So that's going to be your distinguishing feature. So let's talk about clay. We as trace chemists are familiar with kaolin clay and its use as extenders in automotive paint and architectural paint. It's used as well in adhesives and tapes. And so we're used to seeing its absorption bands in the 3600 to 3800 wave number range. But when we have colloidal kaolin clay versus calcined versions of kaolin clay, we have significant spectral changes. And this caught me off guard, admittedly, when I was analyzing samples, because I was so used to what kaolin clay looked like based on my paint background, that when I ran a sample that was labeled by the manufacturer as kaolin clay and I didn't see those samples, I thought I'd made a switch. So I reran the sample, and sure enough, you get the spec that we have up on the top. And I consistently got that, and it's just there. There's just not much there. We lose all of our OH stretches in 3600 to 3800, and we lose a lot of the stuff that's in the fingerprint region. It kind of all coalesces into a single peak around 1076. So this was curious to me. So I wanted to see if the calcination process, which is that superheating process of clay, if it affected the IR spectrum, and it actually does. And there have been studies on that. What happens when you take a material and you calcine it is you're superheating it, and this up to several hundred degrees. And what's going to happen, not only do you have the loss of water, but you have the loss of those hydroxyls. So the hydroxy groups that are on the surface of the clay are going to strip away. And so because they strip away, you lose those OH stretches that are up above the 3500 wave number region. So here is a paper that discusses the changes in the IR spectrum of clay as it goes to higher and higher temperatures and calcination. And we can see that the spectra that is towards the back of this specific diagram is more and more like what we see in the calcine. So what that means is when we look at calcined clay is if it can be completely listed on the product, it can be a major component, and we can be looking right at it, and we're just simply not going to see it in the IR because the OH bands are completely gone, and the other bands really just bands that aren't really going to be diagnostic or very helpful to us whatsoever in identifying clay. So at this point now, we're going to have to look for microscopical properties, which there are going to be some changes to those as well as elemental analysis. And in microscopy, we have to be careful because the calcination is also going to change what the kaolin particles look like. In addition to affecting the internal crystal structure, because we have a loss of those hydroxyl groups, the refractive indices are going to change. And what I found is there's some differences in the literature here. The kaolin refractive indices, just bulk raw kaolin, is pretty consistent. 155 to 156 are the three indices. But if you were to look at the particle atlas and look at calcined clay dust, you're going to see that it gives a refractive index of 1.57. But if you look at the product data sheets that are out there, and these are the product data sheets that they sell calcined clay for various uses, multiple product data sheets list the refractive index for their materials as 1.62. So, and this is kind of what I saw as well within my analyses, that when I mounted my samples in 1.64, I had significantly lower visualization of the particles that I would expect something if it had a refractive index of 1.5. And here is what the sample of calcined clay looked like microscopically. Again, this is calcined clay. And we can see some of the smaller particles as well as some of the larger ones. So let's talk about borosilicate glass. I've mentioned this at least once. This is used similar to what mica is used for. It's not used as an extender, but it's used more for the decorative and the effects. So here we have various forms of borosilicate glass. So we can have calcium and sodium and aluminum that are part of that, maybe even some silver and zinc. But the particles all look the same. They are relatively large individual particles. They really kind of jump out at you. I was looking at a lip gloss last week, and I put a sample on a scope, and I was looking at it through a stereoscope, and you could just see those glitter particles, for the lack of a better phrase, that were fairly large. And once I saw those, I was pretty sure that we had borosilicate glass in the sample, and that's what we did. Borosilicate glass is going to be readily identified by microscopy. You're going to see some of the same colors that you see with the natural and synthetic mica. You're going to have those pastel colors. I haven't seen a lot of the darker oranges and darker reds with the borosilicate glass, but you may have those, but I have seen mostly of the pastels. You have various sizes, but the key feature here that's going to differentiate borosilicate glass particles from mica is that the edges are now going to be very smooth and they're going to be very sharp. The edges are not going to be rounded or irregular. They're going to be smooth. They're going to be sharp. And then when you cross your poles, you're going to have distinct halos of these edges for these particles. So this here is what a borosilicate glass particle looks like. Again, take note of the smooth, very sharp, and well-defined edges that are present. And then when we cross the poles, this is the halo effect that I was talking about. And if you have a sample that has borosilicate glass and you disperse it in 1.64, 1.66, and then you cross your poles, these particles are really going to kind of jump out. You're going to see them in a lot of different places within your sample when they're present. This here is what the IR spectra looks like. Again, we have a very strong silicate stretch, and that's about it. So let's talk about these spherical particles and what these look like. They look just like what I say. They look like these little spheres or balls or beads that are spread out throughout your sample. They can be silica or they can be polymers. They can be polymethyl methacrylate. And you can also have polyester-based spheres, but the ones that I analyzed specifically were silica as well as acrylic. And the purpose of those is that they can be used to, quote, ditch the look of fine lines and wrinkles in the skin. What does that mean? As you spread it across your face, these spheres bury themselves into the wrinkles and fine lines and plug them up, and that way the rest of the material slides over it. So this is a wrinkle hiding product. And also a quote imparts a smoothness and a soft touch if you were to run this product through your fingers. And because now you're using those spheres are like little ball bearings running across your fingers. These are really going to jump out at you microscopically, but we have to be really careful with this. The reason why I say careful is because let's say we have a liquid formulation or even a lipstick or a lip gloss that has oils in there. We can do our particle dispersion. If those oils don't readily mix with our mounting medium, those oils are going to beat up themselves and they can give the appearance of these spheres. And it takes a little bit to tell the difference between the two, whether you have beaded up oils and liquids in your mounting or you have these actual spherical particles. Microscopically, that might be a challenge, but if you mount these and do elemental and look at them through SEM EDS, you're going to see these spheres pretty right. So this is what those spheres look like. These are their silica spheres. And here we have various sizes, and you can buy products that have a range of sizes from fairly small to fairly large. And this here is the polymethyl methacrylate spheres. And again, it's the same thing as the silica spheres. Microscopically, if you just look at them, they just look like little balls. When you analyze those, if you analyze the bulk and the raw materials, they are very readily differentiated. The silica, we got that SiO stretch. And then with the acrylic spheres, we got those acrylic stretches that we are familiar with in other forms of trace. And if we were to do elemental analysis, again, they are easily differentiated. So IR and of raw products, we can tell them apart. We're probably not going to be able to do this in actual formulated products. It's going to be easiest if we do SEM-EDS, just lock the beam on a single sphere, collect a spectra, and see if it is primarily carbon or if you have a large silicon peak in there. But we can also do some differentiating microscopically if we want to, because they can both be present depending on the formulation. So the easiest way, based on refractive indices, is to mount a sample of your material and disperse it in 1.47 oil. And when you do that, your acrylic particles are going to have a higher refractive index than your oil, and your silica is going to have a lower refractive index than your oil. So mount it in 147, zoom in on one of your spheres of interest, and check your Becky line, see what direction your Becky line moves, and that's going to tell you whether you have silica or whether you have acrylic. Unfortunately, I didn't have any samples of the essential polyester beads to see how you could differentiate those. My guess is you're also going to be able to differentiate those using refractive index determination. As far as other components that can be out there, these are not necessarily particle components, but these are other chemical components. Dimethicone can be present at various levels. You're going to see this primarily with a very strong 1260 peak. Lauryl lysine is a surface treatment for various particles. It's going to show up with a small peak at 3329. Of these two, the dimethicone clearly the most prominent component and the most prevalent component. So this is a standard of dimethicone. What I'd like for you to do is focus on that 1259 peak and 1260. There's other peaks there, but this is the one that kind of jumps out in the samples that I've seen. So here, again, to kind of show that, the contribution of dimethicone. In the middle spectra, we have a liquid foundation and then a second liquid foundation that's at the bottom. And you can see both of these have contribution of dimethicone with that 1260 peak. We do have that other peak that's present around 1,000 wave numbers. The problem with using that one is there's so much other stuff that lands in that same area that peak is just not particularly helpful. So this is where we're going to focus on that 1260. You can also use the 2963. That's a fairly sharp band. The problem if you have a lot of CH stretches that are in that same region, that could be masked completely. So let's put this all together. Here's a sample of lipstick. I've dispersed these particles out, and we can see some things that jump out at us. You can see those large plate-like particles. These are large. If we look at our edges, they have well-defined edges that are smooth. They also have sharp corners to those. So this is indicative of borosilicate glass. We have across the poles. What you're going to see is you're going to see that halo around these particles. And then you have numerous spheres. In fact, if you look closely, the vast majority of the particles that are present within this particular sample are going to be those numerous spherical particles. I didn't do the refractive index test to see if these were silica or if these were polymer spheres. Now we're going to look at a lip gloss. This lip gloss it was primarily a liquid component to it, but we also have some individual particles that are present, and it's the same particles that we had before. The point here is to show that they are present, but they are not nearly as abundant as what we had with the lipstick. Same features with this borosilicate glass. We got those light pastel colors, smooth, well-defined, sharp edges, and the spherical particles that are present. Now let's look at a foundation. This is going to be a cream-based foundation, and as we look here, there's a lot of titanium dioxide, and we have some titanium dioxide. We also have some iron oxide that's present. As we were to increase our magnification, we'd start seeing those iron oxides a little better. But what I wanted to show you here is the presence of those spherical particles as well. And these may be a little bit more difficult to find because these smaller TiO2 and iron oxide particles are kind of surrounding it and may hide it a little bit. But if you look close enough, they are present. So let's answer this question. How do we know if this material is a cosmetic product? How do we answer that? Well, these are the various particles that we've looked at. This is another slide that might be helpful if you're so interested, listing the various particles or materials on the left-hand side. And my initial thoughts is a key means of identification, whether those are microscopical features or whether those are IR features, and on occasion, if we're having to look at elemental features. But what things can we look at to increase the likelihood that we're looking at a cosmetic? And I'm going to propose these four particles. If you detect synthetic mica, using fluorine in your SEM-EDS, if you detect borosilicate glass microscopically, and if you find these various spheres. If you find one or more of these different kinds of particles, I'm going to suggest that you're likely looking at a cosmetic. And if I'm asked the question, do we have a cosmetic present? These are the particles that I'm going to be looking for because they seem to be separate and relatively unique or relatively limited use to cosmetic products. One other one that we might see in our spectra is going to be this dimethicone. I hesitate to place this in the same level as the others because of the various uses that dimethicone can be used in other products. It can be used in other larger cosmetic products. Those who've looked at condom lubricants are well aware of its prevalence in those products, as well as other body care products. So if you see it, just kind of mark it, but I'm not sure I would give it the same significance as the others if I'm going to call them material cosmetic. All right, so there are various challenges. There's lots and lots of silicone when we're looking at the IR, and that just means that peak between about 1,000 to 1,200 wave numbers is really not going to be particularly helpful because of how many materials have that SiO bond within those. Another challenge is that the oils and waxes that are present, particularly in the lipstick and the lip gloss, they can really dominate your IR spectrum. So here's an example of a Mary Kay lipstick sample, and all I did was a library search, and the first match is glycerol trioleate. And as you look at this, you can see that the vast majority of the peaks that are present within our sample are attributable to that. So if we have a lot of waxes or oils within the sample, that's really going to potentially dominate our IR spectrum. And what that means is it may limit the value in a QK comparison. Here's another challenge with base components. Here we have a lip color. This is a liquid lip color, and it's kind of like a lip gloss. And again, when we do the library search, we can see that this dimethicone is the largest component within that. And again, the peaks for dimethicone are the largest contributor and most prevalent contributor to the IR bands within our sample. And then we just have limited variability. Here we have the IR spectra of various foundations. And yes, we could find some small differences from one spectra to another, but there are a lot of similarities. And I just got a bit queasy in the idea of trying to be able to differentiate have a really strong comfort level in differentiating one foundation from another just using IR. Now, there are sometimes where you could probably clearly eliminate it, but if I didn't find any differences, the strength of my association is probably not going to be that high. In my scale, it's going to be a type 4 or so. If we look at concealers, similar products, again, we're going to find the same thing, that we have some differences here and there, but we have a lot of similarities, and it's because the same materials are used from one product line to another. Here we have different shades of the same brand. This is Bare Minerals, and these are going to be different colors, a lighter color to a darker color. And in those situations, really the only difference in the formulation is the amount of iron oxide that's present. And what you can see is that the IR spectra are largely indistinguishable. And if we were to look at these microscopically, we might find some differences, but it may be a challenge for us to feel comfortable enough to say that, yeah, we can tell microscopically or even elementally that these products are different. And this leads into the issue with comparison difficulties. A typical comparison is once you have analyzed your question material, either with an individual technique or your full range of techniques, looking at a known standard, doing that direct QK comparison is the typical approach, and there are going to be some issues that we have to take into consideration with cosmetics. That you're going to have a loss of materials just because it's listed on the ingredient list doesn't necessarily mean that it's going to be on the sample that you collected. You can have evaporation of materials. You can have absorption of materials. They were there present initially, but they were gone. You can have contribution of skin or body oils that start interfering or more contributing additional spectral bands. You could have other products on the skin. You could have mixtures. You put a foundation down, and then you put a blush down, and then you put a concealer down. All of those things are going to mix together, so you're going to have a hodgepodge of those materials show up in your techniques. And then the contributions from the applicator, and I'll show you what I mean by that. So here's an eyeshadow. This is before and after wear. The before wear is the purple line. And what I want you to focus on is the peaks that are designated by the blue arrow. Those are present in the original formulation. I had one of my colleagues put it on, wear it for a day, and then we removed it and analyzed it, and that peak completely went away. I tentatively think that is a peak based on the formulation that in the ingredient list, which you could expect that would either absorb or evaporate away, which makes sense on why it's gone. But we also have some other peaks that have shown up in the worn sample. And we see that in a face powder. Here we have before and after wear. The original material is on the top. The material that was collected after it was worn throughout the day is on the bottom. And what I'd like to focus on are these. They're not really strong, but they are clearly present. We have a couple of bands there around 1650 as well as around 1550. And if you're familiar with paint, these are similar to what we have in urethanes. And what we've got here is some of those similar stretches, those amide stretches. So I had a theory that these were associated with either skin cells or body oil. So I took an IR of my skin and compared it to the spectra of the material that was removed after being worn. And we can see that we've got those peaks that are present in my skin tissue that are also present in that sample that was removed. So we just have to be aware of the contribution of the skin. So we have similar spectra for different mixed products. So here, one spectra is concealer that was placed on top of foundation, and the other is a face powder that was placed on top of the foundation. Then this mixed product was collected later on and then analyzed. And when you do the comparison, even though I know that these are completely different mixtures, one with the concealer, one with the face powder, the IR spectra look very, very similar. Yes, there are some differences, but this just shows what happens when you start mixing these products. One of the other things that we have to be aware of is the contribution of the applicator. And I ran into this with this case of mine. When I did my QK comparison, I had a material, I identified it as a cosmetic. I was given a compact that had various eyeshadows on it with various shades. One had a lot that was removed, and the color of the one that was removed in this compact was nearly indistinguishable from the material that was removed from the victim. So when I did my IR, really couldn't find any significant differences. When I looked at my elemental, couldn't find any significant differences, but when I looked at microscopically, they were completely different. The question sample had all kinds of mica flakes in it, whereas the material removed from the compact had no mica plates in it whatsoever. I went back and retested both of them, same results. And I initially called this an exclusion because I couldn't explain the difference. Later on, it dawned on me that it was a single applicator that was used for all the different shades in that compact. So I remember that some of those shades had a lot of mica particles that were present. So I grabbed one of my coworkers' applicators, and it was just an applicator brush, and I just shook it out, and all kinds of stuff came out. And sure enough, there are all kinds of mica particles that were present. A lot of these are silica beads or spherical beads that are present. Here is another applicator, and here you can see what jumps out at me is the massive amount of starch that are in this specific brush, and it's because it was used to apply a product that had a lot of starch in it. So if you have the same brush that is used to apply multiple different types of products, you can see that you're going to have a lot of carryover, a lot of contamination. So ultimately, the correct conclusion in that QK comparison in my case was going to be then inconclusive. And before I could make the change in this specific case, there was a plea that was made. But it just shows how challenging this is. So this here's a summary of the difficulties. A lot of work still needs to be done for us to move beyond anywhere besides inconclusive when it comes to QK. We might be able, in some situations, to make an exclusion, but we really have to be aware of mixed products. We have to be aware of differences in evaporation and absorption. And specifically, if your approach is to look for differences, then and then make an exclusion unless you can explain those differences. When it comes to cosmetics, there might be a lot of reasons why you can explain the presence of those differences. So really, the question is there sufficient published research regarding the discrimination studies for these various techniques? There are studies that are out there. Whether or not those studies are sufficient, specifically when it comes to the mixed products, is something that I'll leave up for you. It's going to be a bit of a challenge if I have another one of these cases come in. You have been incredibly patient. This was a lot of material in a very, very short period of time. I apologize if I moved too fast, but now I'm open to any questions that people may have.
Righty, we're going to turn our cameras and microphones on and head right on into our Q&A. Okay. Thank you, Jeremy. That was a very informative presentation, and as someone who wears makeup, I found that very interesting.
My pleasure.
So we're going to dive right into some of these questions from the audience. The first one is, and I think you touched on this during your presentation, but maybe you can expand on it. Can you explain why ingredients listed on the ingredients list of a cosmetic may not be found during analysis?
Yeah, there are, like I said, I touched on that a little bit, but there are probably a lot of different reasons for that. One of them could be the concentration, and also kind of tied to your analytical technique that you use. If you have a material that's 1%, 0.5%, or even less than 0.5% concentration, that may not show up on your analytical technique. If you're using IR, it's potentially those spectral bands are going to be masked if they're by other bands that are present. If you're looking at particle ID, it may be difficult to find a particle that's at that low of a concentration. Another thing could be your analytical technique that you're using. If you're limited in your techniques based on your lab, that's going to be a challenge. For example, bismuth oxychloride, that is not going to show up on a typical IR run if you're doing it from 650 to 4,000 wave numbers. Because that is an ionic bond, it's going to show up much lower wave number. So it's going to show up on elemental analysis if you do SEM EDS. But if that's not a technique that you use, then that's not going to be something that you're going to be able to find. You can have other products that have overlapping peaks. So as I mentioned there about calcined clay, because the largest absorption is a band that's kind of in an area where you have a lot of other silica peaks, you may not see that at all. And then also we touched on the evaporation. If you have a formulation that contains alcohols or something like isododecane, as that material is applied to the skin, it may end up evaporating, and once you collect it, it's just simply not present.
Gotcha. Thank you for your insight there. Another question that came in is colloidal clay only found in cosmetics, or are there other products that have this form of kaolin?
Yes, the two different forms of kaolin that I discussed, colloidal kaolin as well as calcined kaolin, are found in products outside of cosmetics. For example, colloidal can be used in the pharmaceutical industry, can be used in the manufacture of various tablets and pills. And this here, it's going to be a different grade. It's going to be the USP grade of colloidal kaolin. When it comes to calcined clay, because of some of its thermal properties, it can be used as an extender pigment or as in castables if it's mixed with something that can be extruded, such as the manufacture of certain castable furnitures. So yeah, we can run into both of those in numerous areas outside of cosmetics.
Thank you. Next question. Given the particular challenges of cosmetic mixtures and external contributions, how do you normally report cosmetic results in a report or testimony?
So I'm going to be limited on this when it comes to actual practical experience. I had a single case, and I can tell you what I did with that single case. With this single case, I had mica that had been coated with some kind of metal oxide. I found that. I also found iron oxide particles that were present, titanium oxide particles, and then I also had silica spheres that were present. I used SEM EDS to be able to demonstrate that they were silica spheres. And then I also think I had some small pigments. So what I did is my report said that the analysis indicated the presence of, and I listed those individual components. And then I said this combination of materials can be used in cosmetic formulations. But that's how I reported it out.
Thank you for your answer there. Up next, is it always the borosilicate type of glass, never soda lime? If so, any idea why?
I'm going to plead ignorance on that question. I don't know the answer to that. So if it is only borosilicate, I don't know the answer to it. So I'm not quite sure what the answer is to that question. Apologize.
Okay, go on to the next one. This audience member says, as a forensic nurse who works with living patients coming to the emergency department after things like sexual assault or domestic violence, are there circumstances in which cosmetic analysis have come into play or could?
If you have a cosmetic that's going to be used to cover up an injury, this was the specific case that we had. We had a decedent, and a cosmetic was used to cover up injuries on this individual's face. It was a child who had no reason to be wearing cosmetics, so that's why we used it. So if there is a forensic question as to why cosmetics are being used to cover up injuries, such as bruises or other things, that might be an opportunity where you could collect it. The collection is a whole nother challenge. We did two different approaches. We tried scraping the skin, which we ended up just abandoning really quickly because that picks up a lot of skin and other debris that was going to get in the way of the analysis. I'm not a fan of collecting things by swabs, but in this case, that was just the approach that we took, because my thought was I'd rather them successfully collect it on their end, and then on my end, I'll worry about getting it off the swab. So it did make it a bit of a challenge on my end, but that's how we ended up deciding to collect that material.
Thank you for your answer there. Next question. If IR still makes different brands of the same product difficult to differentiate, how does elemental analysis do in comparison normally?
So that can also be a challenge, and it's really based on your comfort level. So let's say we have a product that we have different shades of the same foundation or different shades of the same face powder. And those different shades are largely based on different concentrations of iron oxide. So now all we're looking at is how much iron is present. And for me, I'm not real sure that I'm going to be particularly comfortable making a call on differentiating different shades based on iron oxide concentrations. This is probably an area where we could certainly do a lot more research. I did do a study earlier this week on different shades of lipstick. So I looked at a product line from Wet n Wild. My daughter happened to buy a whole bunch of those for a girls' party, so I grabbed some of them. And there were 4 different shades that I looked at, and the IR spectra from all 4 of those lipstick shades were very easily differentiated. They were also easily differentiated microscopically. So elemental analysis might be able to help you out, but just remember the other difficulties that besides different formulations is other products that are layered on top of it. And is that difference because you have different products, or is that difference because you have another material that's been added on top of it?
Yeah, thank you for your insight there on that little anecdote. So you mentioned dispersion in order to view the particles. What techniques did you use to view the particles under the microscope?
Okay, as I had mentioned before, my microscopical techniques are skills are not on par with a lot of others who may be listening in. So what I use bright field as well as a polarized light microscopy. The magnifications that I've primarily focused in on are 200 to 400 times. I could bump that up to about 600x if I needed to, but those are really the 2 techniques that I focused on. If for those of you who are more trained and better trained in conoscopy, you could probably expand into that, but that's just not a technique that I have anything beyond a general introduction.
Thank you. Next question. Have you considered approaches for pigment particle analyses besides PLM?
Yeah, that is something that I would really like to look into because some of these pigment particles are fairly large, like with this lipstick. In addition to seeing some of the silica, or not the silica, but the borosilicate that was present, as well as some mica, you could see some visible pigment particles, various sizes. Raman would be an excellent technique to use in these samples. If you're able to get a big enough particle, you might be able to do MSP. This is just something that I don't have Raman at my lab, so I can't utilize that technique. Labs that do have it, this is probably something that you could look into. For MSP, it's just something that I haven't had the time to look into at my lab.
Thank you. Alrighty, and following up on a previous answer you gave, how would you prefer cosmetics were collected from a person's body? And is there anything specific you would want to know for testing purposes?
For me, I'd want to know what part of the body it came from. If we're talking, was it pulled directly from the face? Was it pulled directly, from the lips? As far as collecting, like I mentioned before, the best way that we have found is using a swab. If you've got sterile swabs or DNA-free swabs, those are going to be the best. If you'd like to send a blank swab, that's also good because depending on the technique that I use to get the material off the swab, it might be nice to see if any results that I get are based on the material itself or background noise from the swab. But that seems to be the best way to collect it. It's not ideal, but I don't want to use like a trace lift or any adhesive to pull it off, because then I have to get it off of that adhesive, and that's going to be a real challenge. So swabs are the best.
Gotcha. Yeah, thank you for your insight there. Right, next question. Are there different formulations for the same products if they're produced in different countries? Can that be used to determine the origin of the cosmetic?
Again, this is one of the questions that I don't have enough background knowledge to be able to answer that one. Perhaps, but we're limited in enough knowledge as it is to be able to differentiate one product from another, but to differentiate the same formulation but manufactured in different source countries. I'm not sure if we're there yet, but again, I have limited knowledge.
Gotcha. Yeah. All right. And up next, have you looked at any different shades or colors within a single product line?
The one that I looked at the most or recently was this this product line of lipsticks from Wet n Wild. And interestingly, every single one of them has the same ingredient list. But it is that may contain that is what differentiated, because it'll list all of the pigments that are used at some point within that product line. I had, that may contain says it may contain mica. Well, I had one sample that had absolutely no mica in it whatsoever, but I had 3 other samples that did have detectable mica, but the mica wasn't the same. One mica looked like it was titanium oxide coated, and another mica was an iron oxide coated. So you can't just look at like the product line may have the same ingredient list, but differentiated based on that may contain.
All righty. Questions have stopped coming in. I think we're going to go ahead and wrap up right near 2 o'clock. Thank you so much, Jeremy, for being here with us today and for taking the time to provide such a wonderful presentation. Before you leave today's webinar, we would like for you to participate in a short 5-minute survey. Simply click the checkbox icon directly above the chat to access the audience feedback survey for today's event. Your feedback is critical information that helps us improve our webinars and continue providing you the best experience possible. If you would, please take a few moments to complete this survey. We would greatly appreciate it. Lastly, across the top of the live stream window are links to our social media profiles, including Twitter, LinkedIn, and Facebook. There is also a link to our website at forensiccoe.org, a link to listen to the FTCOE's podcast, Just Science, and a link to sign up for the FTCOE newsletter. Like, follow, or subscribe to stay up to date with everything the FTCOE is doing in support of the forensic community. Thank you again for attending, and we hope everyone has a great day.